The next topic which was scheduled for today is coordination complex. So let's quickly, you can see the screen.
Yes, ma'am.
Yes, ma'am.
Learning outcomes. There on the screen. Students appreciate the postulates of Werner's theory of coordination. Like I said, we are not going to teach coordination complexes. We are just going to discuss what are the aspects that we definitely need to transact. Of late, I'm sure my teachers will agree with me. Of late, the favorite question has been like complex COCl3 dot 6NH3, and they've said it gives 3 moles of
AG.
Yes, AgCl when treated with AgNO3. Based on they give this may purely based on how Werner's theory talks about the secondary, primary, and the secondary valencies. So from there, they ask the child to write the structure, the IUPAC name. So that part, though, is not much used, but then good questions from there. So appreciates the postulates of Werner's theory of coordination compounds, which is very, very important. Student is able to define the various terms relating to coordination compounds. This is another outcome that we expect. Like the favorite is denticity. How do you think we would define denticity? It's one of the terms. So it's a kind of we know what it is. We know what is denticity, but then how do we put it across to children? What do we say denticity is? It's a lot of power fluctuation. Yes. How do we define? And if the teachers could, how would we explain denticity? Or if you're asking them to define in a phrase, how would you define it?
For us, 2 hands are there.
Okay.
I think so. For animals, they have 4 legs.
Okay.
Octopus 8.
Okay. That's
So
nice.
unidentate means only one head, like that. We can call it.
Okay. Dentures. Related to dentures. Dentures are the oral cavity, the tooth in the oral cavity. So how we grasp, how we take a bite. Also, you could say a bite of an apple. How many imprints of the teeth you see on the apple also could. Yes, ma'am. Yours also sound. Your explanation also how we grasp things. We talk about Spider-Man also. They immediately relate to. So how would you define denticity? Unidentate, yes, child. You would. Typically in a phrase, how would you define denticity, ma'am? Any others also? Any other teacher also can give us the input?
Yes, ma'am.
Yes.
For bond order 1, the molecules like H2, they can form only 1 bond between them, ma'am. But in oxygen atom, they can form a double bond between 2 oxygen atoms. But in nitrogen, they form 3 bonds, ma'am. Just like that, a single ligand bind with CMI with 1 or more bonds, ma'am. So when a ligand bind with the CMI with a single bond, they called monodentate. When they are bind with 2 bonds, the dentate is bidentate, ma'am. Ligands like EDTA, they can form a single ligand with CMI 6 bonds, ma'am. That's why EDTA is called hexadentate, ma'am. That's why we can define the number of bonds, coordinate covalent bonds between the CMI and the ligand is called
Okay.
coordinate.
CMI understand the central metal ion. Am I right, sir?
Yes, ma'am.
Yeah. So the number of coordinate covalent bond a ligand can form with the central metal ion is its denticity.
Yes, ma'am.
All of us agree to that?
The number of electron pairs that
Number of electron pairs that an electron can share with the CM central metal.
Because every bond contained a pair of electrons. That's why we can say that, ma'am. That's also. That is the correct
Right.
definition. Yes.
Right, sir. Very nice, sir. Now coming into the ambidentate ligand. This is another term which is frequently, ambidentate nucleophile. After that, ambidentate ligand.
Yeah, single ligand can bind in two different forms, ma'am. Like thiocyanide, isothiocyanide, ma'am.
Nitrito and nitrito and.
Yes,
If
ma'am.
I am going with my child in a road, I can hold him in the right hand side. Otherwise, I can hold him in the left hand side also. So that like ligand is ambidentate. Like
Very
that.
nice. Super example, ma'am. This is what I'm expecting. This is what is the whole interaction want to be like. We want it to be like this. How do we relate it to children? Because relating or connecting children to chemistry is one of the most toughest job as chemistry teachers, I'm sure all of us experience. They come into class 11 with the, this big fear, apprehension about the subject itself. So it becomes our moral responsibility to make sure we connect it in such a way that they relate it to their day-to-day lives. Ma'am, your example, Bhanumati ma'am, I'm definitely going to use it for the class next time. When
Thank you.
we talk about holding a child on which side, through which side it is you're connected.
Yes.
Here, we have to remember it is between the central metal and the ligand.
Yes.
Ambidextrous also. We can also talk about ambidextrous. Many people misunderstand ambidextrous. They understand ambidextrous to be people who can write with both hands at the same time. No, it doesn't mean that. Ambidextrous are people, those who can write with both hands. So all these movies give wrong information to be wrong information for ambidextrous people to be who can write like this. And it's not that. They can write with both hands the same way. That's ambidextrous. From there we get ambidentate ligand that we can connect it to that. That's what I'm trying to tell you. So yes, where a ligand, do we all agree that ambidentate ligand is a unidentate ligand? Or is it a bidentate ligand?
Uni.
Unidentate only.
It's a unidentate ligand only. At a time, it can only ligate to one site, one atom.
Yes.
It cannot do that both. So that's where
At the
we need
time,
to be
only
very
one
clear.
atom can act as a
Correct.
donor.
Yes, correct. So that clarity child needs to be given when we are talking about ambidentate ligand. So that was
But they are confusing the dentates. That means ligand C and the ambidentate, ma'am. They are confusing them in our school students, ma'am.
come again, sir. I didn't quite catch you. Come again, sir. If anybody else got him?
They are confusing the ligand C and the ambidentate nature, ma'am.
Ligand C,
And ambidentate nature, I think, like
Yes.
didentate and ambidentate, no?
Ma'am, the definition of ambidentate ligand is not very clear in the text. When we normally say, we say ligand which can donate electron pair either through one atom or part, no, or from the other atom of its composition. That is not very clearly given.
Okay.
Ambidentate ligand definition is not very clear. It more or less sounds like a polydentate ligand's definition.
Okay, so I understood. Denticity and ambidentate ligand. The fact that it is unidentate and the other ligands which a single molecule can ligate to two or more sites. Am I correct, sir?
Yes, ma'am.
Yes, sir. So the coordination number is a little different, no, sir? From how would we define coordination number?
Number of pair of electrons shared between CMI and the ligand, ma'am.
Number of coordinate covalent bonds, correct, sir?
Yes, ma'am. Yes, ma'am.
The coordination number is number of coordinate covalent bond, and that is in general coordination number is with respect to the metal, isn't it, sir?
Yes,
The same
ma'am.
with respect to ligand is its denticity. Am
Yes,
I correct?
Yes, ma'am.
When we talk in terms of metals perspective, then we say coordination number. The number of coordinate covalent bond the central metal can form with the ligand. And denticity would be the number of ligating sites in a molecule,
Yes, ma'am.
coordinate covalent bond that can be formed between the ligand and the metal. So the definitions in this chapter, they play a very important role in not just examination point of view, but to understand the lesson itself more clearly. Correct me if I'm wrong, the definitions come handy for understanding the concepts also. So it becomes very, very important for us to make sure that they are clear with the definitions. We need to spend at least 2 periods for definitions, especially when we are going through denticity, ambidentate, polydentate structures have to be drawn definitely. EDTA, they enjoy actually. Children enjoy this, the structure of EDTA. It looks big. And when we draw the structure on the board, so one methodology is put it on the board. It's okay to make mistakes if you are drawing the structures. So that's another learning outcome. The third is name coordination compounds using the rules of nomenclature. Again, one paragraph, 2 page actually, not 2 page, 1 page of only rules. I'm sure none of us ask children to learn that. How do we take this forward? How do we teach this? Do we read out the rules?
No, ma'am. We can
No.
explain by by few complexes, ma'am.
Correct. That's the best way and the
We can
time-saving
take-
method, sir. Easy
Yes, ma'am.
method is to draw
Yes,
the
ma'am.
structure on the board
Yes,
and then elicit the answer from students. Then just compare it to a simple salt where we have a simple anion and a simple cation. Compare
ma'am.
it to a complex which is simple cation, complex anion, and then opposite. A complex
ma'am.
cation and a simple anion, and
You
both
can take that,
anion and
three
cation
examples.
complex.
Yes, ma'am. Anionic complex, cationic complex, and complex compound, ma'am. We can take.
Different they are.
Yes, ma'am.
Each one and try to do. That's the
Yes,
best
ma'am.
way, sir.
Yes,
That is the best way. I also understand. sir.
I took potassium hexacyanoferrate for cationic complex and tetramine copper 2 sulfate for anionic complex, and one more example for complex compound, ma'am. That's why they can follow the rules after they memorize their names first, ma'am, for these 3 complexes. Then they can apply for other complexes. After
Correct, sir.
they can understand the rules, ma'am.
Yes, sir. What I normally do is on the right hand side or the left hand side of the board, I write the name of the ligand and this formula like hydroxo, oxalato. I write that all the negative ones and then the neutral ones I write down and I give the names. Then I kind of use the method of quizzing also. I divide the class into teams and I give them structures to come up. Which team gets more number of structures, more activity-based nomenclature exercise. They really enjoy. I don't know, somehow of all the inorganic chapters, coordination complex is students' favorite. They really, really enjoy coordination complex, especially naming. Even the students who are generally averse to chemistry itself, they like inorganic, and in that they like coordination complex. So how we put across nomenclature is very, very important, because 100% guarantee there is going to be a question on nomenclature in the board exam. Did we have any questions in nomenclature this year, ma'am? I think there was more question on VV theory and CFT. There was not many questions. Isomerism was not there for evaluation at all. We don't have isomerism again this year, isn't it, ma'am?
They gave, yes ma'am, one question was there. Write the formula of the complex using IUPAC norms.
Okay, only one question was there, ma'am.
Yes ma'am, in 2 mark question, 1 part.
One part.
3
Nomenclature is
mark question,
normally
1 part.
3 mark question, 1 part. Yes.
Yes ma'am.
Ma'am,
So
this year isomerism will be there, no ma'am?
Ma'am, this year will be there.
Ma'am, 2021 it was not there.
Not there, yeah.
21, 22 ma'am is there.
22, 23 it's there.
22,
madam.
23 it is there. full
Yes,
lesson.
yes ma'am.
2021, 2022 it was not there.
Not there.
Yes ma'am.
Right. So nomenclature, how we take it forward depends on how comfortable we are with it. So exhaustive questions are there in the textbook. More than we want, what we want is there. We needn't go outside also. As an assignment, we can give extra questions from other books, but our textbook itself, we work it out. It is more than enough. We can easily help children, make them comfortable with nomenclature. And now students will be able to identify different types of isomerism. That's another outcome, learning outcome. The structural and stereochemical isomerism. Structural also, I finish it very quickly in 10-15 minutes. What I do is, once they are comfortable with nomenclature, at least 3 periods, exercise nomenclature, follow them. Then what I do is, I write down the 4 structural: linkage, ionization, coordination, and solvate on one side of the board, and on the other side of the board I write pairs. I write 6 pairs and ask them to match. So that way also it can be, I wouldn't teach the topic at all. Just try to understand the phrase ionization, isomerism. Just give them a key point there. Key point there. So they will linkage. Just give them the key point. Say ambidentate. And when they see the complex structure wise, they easily connect which is which. So that's one technique, a methodology that we can use. Different, that is a comparison. Comparison is another methodology that can be effectively used in the class. I would say comparing the complexes itself, how different they are with their. So this also can be, you needn't teach it at all. You can make it as an activity in the class. This helps a lot. Or you could, like sir was saying, introduction of complex also you can do with an activity that form the tetraamine complex in the lab also, because potassium ferrocyanide and like sir was mentioning tetraamine copper 2 sulfate actually is one of the confirmatory test of copper cupric ion in the salt analysis. So we could make use of their previous knowledge and help them recall. So the recall is another methodology. Help them recall from the complexes they already know. So another learning outcome, students will be able to finish that. Stereoisomerism, geometrical and optical is the tricky part there. Totally, there are only 6 structures in the textbook, correct? I kind of use that as a bait to lure them to learn those. But then, unless we are thorough, question like a square planar complex of platinum with 4 different ligands shows cis-trans isomerism. When we say that, because when we say metal A4, A3B, metal AB3, they don't show cis-trans isomerism. When we say metal ABCD shows cis-trans isomerism, they are not going to agree with you unless you tell them how. You agree? When we talk about geometrical cis-trans isomerism. So isomerism can either crash our attempts or can make it a success. So very cleverly, keeping COVID in mind, CBSE slashed off, cut off isomerism in coordination complex the academic year 2021-2022, because online it could have been made a success, but then not every child in our countries has got access to devices. So they didn't want to take a chance there, and the teacher's presence is very important to do that isomerism part of this chapter. So this is a tricky part, especially the optical also. When we say bidentate ligand, the metal LL3 hexadentate ligand, or coordination number 6, I'm sorry, coordination number 6 with bidentate ligand showing cis-trans isomerism is also very tricky to explain unless we are clear about it. We show the non-superimposable mirror image for optical isomerism. So student being able to identify the different isomerism is the challenge in this chapter actually. That is a very important learning outcome. Then students will be able to predict the hybrid. This is again a favorite part. A typical board question. One, I don't know if you all remember, 3-mark question, 9 facts was asked one year. Hybridization, structure, magnetic property. For 3 complexes. We had a tough time dividing the marks. You remember, ma'am? 9 facts.
9 value points for 3 marks.
3 marks.
Then we had to bargain.
We had to bargain and we had to say 2 value points. I still remember, ma'am, when ion is not written in nomenclature, if it's an ionic complex, ion part of the complex, we used to reduce, ma'am. We used to give 0. The child writes just the ion, hexacyanide, ferrate, 2. Ion is not written, no mark. So we were going at that level of correction. Now I'm sure some teachers are still following, seasoned teachers still follow that. So this chapter could result in child losing marks, but the child would have come out happy, feeling happy that I've done all the questions. So we need to be very clear while giving input. We need to be very, very clear when we say that this part has to be definitely written. So predicting hybridization, structure and structure of coordination compounds using VB theory, and also structure, or I would say CFT. I'm not talking about structure to CFT. I'm just said a theory itself, VB theory and CFT. So these are only two. Apart from that, we have the ligand field theory, which we do not, molecular orbital theory, which is not discussed in the textbook. But then a small glimpse of that, just to as a to make them think, read a little beyond the textbook would always help. An application of coordination compounds is what I normally start the class with. Introduction to the chapter itself, we start with the application of coordination complexes in the field of medicine, in the field of biology, when we relate it to them, the heme molecule, the cyanocobalamin, chlorophyll. When we talk about biological systems itself, they relate to it quickly. So apart from that, we have metal carbonyls. It's a small part which is mentioned there, apart from stability, which is also the last part of the lesson. So they are basically related to factors contributing towards the stability of a complex. So these are basic expected outcomes from this chapter. Key points, definitions, nomenclature, isomerism, VB theory, CFT, bonding in metal carbonyls it's a mistake there, it's not carbonates, carbonyls, and applications. Methodology, like I said, recall, inquiry-based instruction, visualization, very important visualization when we talk about isomerism. Flipped classroom. Flipped classroom is you give them a topic, like I said earlier, in B block also we can do that. We can ask them to come prepared with structures and then do a concept and then discuss it in the class. That could be quite effective also. And some children who take up extra coaching, they could contribute a lot towards explaining to the peer group. That way also we can make the classroom a more interactive one. These chapters are best learned from each other as well as from the inputs from the teacher. And I always feel when children start learning on their own and our role becomes minimum, that is the best. I think we are the best then. It's not necessary that my presence has to be felt. The child should feel, oh, without chemistry ma'am I cannot do. No, I can do without her. She's taught me the technique to use the textbook. If we can translate that to children, if we can empower children that way, that they are comfortable without our presence and they're able to take it forward, because higher studies, all of us will agree, we are on our own. It's only till school that we handhold children. After schooling, it's purely how the child uses the resources. So that level, 11th and 12th, we should bring in, including me. I also feel there are many times I feel I have to literally handhold the child, spoon feed him, give him written material so that he feels comforted. But that does not actually help him. It probably would, give him a little more confidence that I have got something to ready reckoner. I have something on my hand. But then when he's made independent on his own to take up a concept, understand it, with so much of on the cloud, so much on the internet, he can help himself. The one thing that we near where our presence is needed is to give him that our experiences, those small places where there are contradicting facts, the conflicts. Only there he might need our help. Otherwise, he will not need or she will not need our help. We need to slowly detach ourselves from, always hand holding them. Give them more exercise, more questions to think about. That's another methodology. So classroom discussion comes only when we have given them some input in terms of questions. So these are some methodologies which would work for this chapter. Isomerism, I just went on to, I'm not going to speak about reflections. We've already said reflections and assessments are purely going to be tests and, like I said, quiz, competition wise quiz in the classroom. So you're the boss when it comes to creativity of how you can make the class interesting. I thought we'll spend more time on these isomerism aspects. Anybody would like to say something about it? Like I said, complexes and pairs could help them understand. A flow chart like this gives it in a nutshell. The textbook, it goes paragraph wise. One very good question where we say ionization isomerism, a very favorite question, is about how the complex is treated with barium chloride and silver nitrate. How do you prove that it is how do you identify the isomerism using these tests? Remember that questions there in the in-text also, barium chloride and silver nitrate. If the ligand is sulfate and the ligand and the counter ion is chloride or bromide. Anybody remember that question?
Yes,
It's a very important question.
And children often know point out that sulfate is a ligand and in the other complex bromide is a ligand, but that doesn't fetch them the marks. It's the
Correct.
complete test which they have to write and score that marks.
Yes, we say white precipitate of barium sulfate when it is counter ion, whereas when it is inside the coordination sphere, it is a ligand. So it does not give the white precipitate. So generally this is complete reaction, not complete as such, but then showing barium sulfate and silver chloride. If it's chloride or bromide, if it's pale yellow, it's bromide, that has to be shown by the child. So in isomerism, that's one possible question. In structural isomerism, that's one possible question.
In fact, in entire chemistry, the distinction has to be answered in a very beautiful way such that they don't lose marks. The children know a lot more, but what should be written to get the marks, they sometimes miss out.
Correct. A classical
write,
example, Lakshmi ma'am, is that iodoform test.
Yeah, they write the formula of the compound form, but they don't write the precipitate color and finally end up losing marks.
Yes, in fact, ma'am, if you remember, the children write the balanced equation of iodoform without mentioning yellow precipitate anywhere. And though they are better off than the children who just wrote yellow precipitate, who get that 1 mark, these children lose that 1 mark because they have not mentioned yellow anywhere. So it's our model again at this point. Very important for us to answer question based on observation, visualization, appearance of a colored precipitate, smelling gas, or effervescence. So clearly talking about the observation which helps us identify a compound. So normally what we do is we give them a tabular form and we say reagent becomes very important. In a distinguishing test, reagent is very important, and the color or the different, what is the observation that is noticed is very important. We have to make sure, I'm sure when Sindhu ma'am talks about organic chapters, she'll come up with a very important way how we answer questions when it comes to identifying or differentiating between compounds. Very quickly, optical isomerism, I thought we'll touch upon a little. So there are, like I said, in stereoisomerism, only 6 have been discussed. There's always this doubt about flipping the molecule. How do we say it is non-superimposable? Anybody, any inputs on this? How do we say this is non-superimposable? This is always a contradiction for children. Always they want clarity on this is non-superimposable. How do we tell them? How do we identify non-superimposability of an object or a structure over
students? We can ask the students to draw the two opposite isomers in 2 different papers, ma'am. We can put the one into in another structure, another paper, ma'am.
Okay,
but here, if we put like that, Cl ligand at the right top cannot match with the En, ma'am, ethylene diamine. That's why that is not superimposable, ma'am.
like this. Am I right, sir?
Yes, ma'am.
Right. That's a good method, sir. That's a good method. How do we say D and L isomer? If they say, how do you know that this is D or L isomer? How do we answer that question, sir?
Take D and L only we can buy through experiment only we can.
Correct. Yeah, we clearly say we need a polarimeter to identify the D and isomer. If one is D, the other one is L.
Yes, ma'am.
Yeah, we don't say.
It's a trans only by observation, ma'am. But otherwise, we can use only by polarimeter in laboratory only we can determine.
Lakshmi ma'am, you're saying something? ma'am?
I normally make a temporary model for that. Whenever the optical isomerism has to be taught, particularly for these didentate ligands and all, I make a model, a small model, where I combine 3 sticks, make a octahedron kind of structure and connecting points,
Mhm.
and take it to the class and show that if you rotate it also, what is outside is what is inside.
Mm.
Like the ethylene diamine on the left, if you just take it on the next sheet,
Flip it,
flip it and rotate it by 180.
180 degree.
Yeah, so the ethylene diamine in the second structure is inside on the top, whereas ethylene diamine would project outside the board in the structure that we have taken after
Correct.
rotation. So
But
I
good.
normally take a temporary model for that class and show them how it works.
Yes, ma'am. Super. Visualization methodology really works in these situations. So good, ma'am. Even I'll try working it out. I normally go by charts which I prepare, but then again it's only on the paper.
What they do is they will draw a line through the 2 chlorides and they will say, ma'am, there is a plane of symmetry.
Yes, they'll do that.
So to show them that it is not a plane of symmetry, that model works best.
Yes, ma'am. Very true. Very true. Thank you for sharing, ma'am. We'll all try that for the next class in coordination complex. Again, this is another one which really intrigues many students. This is what I was talking about, where we have coordination number 6, where children make a lot. When they say En in brackets 3, they very difficult for them to relate that it's a didentate ligand and not
Coordination
textbook.
number is
Yes, coordination number is 6. So here, optic and in our textbook, I don't know why they have gone for a flower petal kind of.
So it's an exaggerated balloon-like structure. At
Yes, that actually supposed to give them a kind of sense of comfort, but it doesn't. They are very busy drawing that shape.
Yes.
They keep rubbing and keep drawing that shape. Not necessary. They can take it as simple as this, but they keep drawing that like this, and they go about drawing that petal, which again they make a lot of mistakes in understanding and depicting this. And another very important point is when a geometrical isomer is asked, they are asked to draw the charge there. The charge there has to be clearly indicated if it's an ion. If they miss out on that, they lose marks also. There also. So if it's an ion, if it's given with a counter ion, then you write the counter ion adjacent. But generally, these complexes are not given with a counter ion. So we need to encourage them to write the charge. So the next, this is the geometrical isomerism. Like I said, metal ABCD. How do we talk about cis trans? There are 2 cis and 1 trans. Am I right?
Yes.
There are 2 cis and 1 trans. How do we explain this to children? How do we say 2 cis and 1 trans? This is actually a textbook question. This is an exercise question in the textbook. How do we say cis and trans here? It's the only challenging question in our textbook in terms of isomerism. When I say geometrical isomerism.
What we do is we take, let us say, bromide and chloride as reference.
Yes, ma'am.
Fix bromide. Fix bromide, ma'am. Let's fix bromide and keep moving the other ligands.
I actually fix 2.
Okay.
I take, say, bromide and chloride. So if you look at the first and the third structure, the bromide and chloride are adjacent. Bromide is adjacent to pyridine, whereas bromide is adjacent to ammonia in the third structure.
Correct. So first and third are cis, and first and second are trans.
With respect to.
Yes,
so I tell them, then children will come out saying that, ma'am, then ammonia and chloride also, we will have 3 more structures. Then I would tell them, from these structures, pick the structures which have got ammonia and chloride in adjacent positions.
Correct. So again, ammonia and chloride, 2 and 1 are cis to each other, and 2 and 3 are trans to each other.
So pick
We can,
two,
we can fix it with 1 also. We can do it, ma'am. We can do it with 1 or fix 2 and then rotate the rest and compare 2 and see how they are with relative positions of each ligand. So this is another part where most of us kind of take some time to convince people, convince students in class 12 level. So they need to figure out. We ask them to give the ligands, pick the pairs. When we ask them to pick the pairs, they'll be more convinced, or they'll think you are making it convenient for you. You're giving a more convenient way of looking at it. Let us look at it. So encourage students to look at it. and try to figure out. So this is the part, the isomerism part can actually, can actually make if the child gets it right, the whole chapter is a success, according to me. So isomerism plays a very important part. I take extra care when I go into the class for 2 sessions or maybe 3 periods for isomerism. I take a lot of care to do it. In VV theory, I've just taken some aspects which is there in the textbook only, some examples as well. This is the easiest part to communicate, isn't it? There are 4 examples given in our textbook.
Yes, ma'am.
sp3 hybridization, dsp2 hybridization, and d2sp3 inner orbital and outer orbital complex. sp3d2 and d2sp3. Both all the 4 examples. All the 4 examples are given in our textbook itself. So explaining with that itself, again here configuration becomes very, very important. Always encourage children to write electronic configuration and then figure out the hybridization and shape. It's the best way. And thankfully we have coordination number 4 and coordination number 6. In coordination number 4 we have square planar, DSP2, and coordination number 4 we have SP3 tetrahedral. And coordination number 6 we have SP3D2 and D2SP3. Here many of us, I don't know, at least I miss it many times to mention inner orbital complex and outer orbital complex. This is very famous question on VV theory which is asked about nickel. Anybody remember that question? Nickel never forms
Low spin octahedral.
low spin
Octahedral complex.
low spin octahedral complex. Low spin octahedral complex. That means it again low spin as in the hybridization is never D2sp3. Am I right, ma'am? Many children write that as an answer. Nickel never can form D2sp3 hybridization, even with ligands like ammonia. How do we answer this question? Nickel will never be able to form D2sp3 hybridization. It never forms inner orbital complex. Whatever the ligand, it is always outer orbital complex. It's always sp3d2. How do we explain this? 3d8, 2 plus is 3d8, argon 3d8. So it will have one phrase, one liner. The answer is one liner here. Why nickel does not form low spin octahedral complexes? Anybody? Urmila ma'am? Whatever the ligand, nickel cannot make available 2 empty d orbitals. Even upon pairing, only 1 empty d orbital will be available. Whereas for D2sp3 hybridization, we will require 2 empty d orbitals. 3d orbitals, 2 should be there for D2sp3 hybridization. Am I right, ma'am? And this child can figure out himself when we encourage him to draw VV theory box diagram. Electronic configuration below that box diagram works best. When he figures that out himself, that was if you remember, higher order question that year, isn't it, ma'am? Hindu ma'am and Lakshmi ma'am, if you remember that particular year, that was a higher order question. Nickel does not form lower. Children wrote nickel does not form D2sp3 hybridization. That was another added part to that same question. It was not the answer for the question. Did we give marks, ma'am, when the children wrote D2sp3 hybridization is not formed? We didn't give marks.
No.
Yes.
We gave marks only when when the child said that even upon pairing, there's no nickel is not nickel cannot make available 2 empty d orbitals. 3D orbitals. That's why it never forms inner orbital complexes. So VV theory can again, like I said, children favorite if you know how they know how to handle it. The best way to handle is always go with us teachers writing the electronic configuration on the board along with the box diagram. Electronic configuration of the ion, hybridization, showing the hybridization on the board, everything comes up. No need of writing anything at all. Hybridization, hybridized orbital overlaps. Because it's generally when we have ligands like ammonia or water or Cl, it's hybridized orbital overlapping with hybridized orbital. Am I right? Hybridized orbital overlaps. Unlike F or Cl, where it is atomic orbital, hybridized orbital overlap. When we take ligands like ammonia, Cl and all, it is always hybridized orbital overlapping with hybridized orbitals. So that overlaps when we mention 6 of them, and number of unpaired electron automatically emerges out of it. So they can easily identify whether it is low spin or high spin complexes. So paramagnetic, diamagnetic can be identified when we just draw this electronic configuration, box, hybridization depending on the ligand. Again, one point to be taken care here is child never mentions that Cl is a weak field ligand. So pairing up does not take, because VV theory is one of the limitation is it does not classify ligands as weak or strong. So with the knowledge of CFT, the child has to predict whether pairing will take place or not. So upon pairing, that's how it's mentioned in our text. Upon pairing, they have shown the paired state. Child should not comment about the ability of the ligand to pair up. So
That's one thing, ma'am. Always, even if we tell them not to write strong ligand, weak ligand under VBT, child again writes that very often.
Very often,
Yeah.
but it is VV theory does not classify ligands like that. So that's very important that we need to communicate to students. So I think VV theory is once you finish isomerism, it's then after that it's a smooth cruise through the end of the lesson. And CFT, I've just taken the octahedral splitting, crystal field splitting. Tetrahedral also is mentioned, and in questions of copper sulfate pentahydrate, where copper sulfate pentahydrate, this work comes very handy when we try to explain colors. This itself is a question. I think this board exam they had asked the splitting, isn't it, ma'am? And they had asked electronic configuration of 3D4 when pairing energy is greater than delta O. Am I right?
Yeah, we
Yes,
had
ma'am. D4.
D4
Delta 0 less
configuration.
than T.
D4.
D4. Pairing energy is
Delta
greater.
is less than pairing. Yeah, pairing is greater.
Pairing is greater. When pairing energy becomes greater, pairing does not take place.
Yes.
Am I right, ma'am?
Yes, ma'am.
So again, working on the board, that methodology works best. And children love this diagram. And if you don't write the scale, energy scale moving upwards, they don't get marks. So let us always remember on the board, we first draw the energy along the y-axis, energy scale along the y-axis, and say energy increasing in the upward direction. The child doesn't draw it, just shows the splitting, 0, no mark. So these are the things, though easy, child could lose marks if we are not careful. And we need to do it on the board first. So use of board should be exhaustive in inorganic for writing equations, for drawing structures, formulae. We need to use the board. It's okay if we make mistakes. It's okay, because child will understand that anybody can make a mistake, and from mistake we can always correct ourselves. So I'm not going into details of all this. We all know. We all know how to teach this. In fact, we love doing this because children understand this better. When we draw the 5 orbitals and show them dx, dy, and dz, that 5 orbitals, and say dx square minus dy square and dz square are along the axis. So the repulsive forces are, and we show that octahedral splitting, those 2 orbitals go up. I'm sure we draw it after drawing the d orbital double dumbbells and go ahead. It's not given in the textbook, but it's better we draw and show. And like I was saying, color is best explained by CFT. In fact, it is the best theory to explain color. And one phrase which everybody loves is DD transition. So let us just take a couple of minutes to understand what DD transition means to us. What is the meaning of DD transition? I would like some clarity because textbook says DD transition everywhere. And I got stuck once when we were trying to understand the structure of copper sulfate pentahydrate. Copper sulfate pentahydrate is coordination number 4. Am I right? Coordination number 4. And we have octahedral splitting and tetrahedral splitting in the textbook. But copper sulfate pentahydrate is coordination number 4. The ligand is water. And on heating, water is lost. So degeneracy of d orbital is restored. No DD transition takes place. But then when we say this for titanium, it works. But for copper, it will not work in the textbook because copper 2+ in copper sulfate pentahydrate is a square planar complex. Am I right? And square planar splitting is into 4, not into 2. Into 4. That is not there in the textbook. So how do you explain? There is this line in the textbook. Copper sulfate pentahydrate does not undergo DD transition. In page number 260. They've given titanium complex Ti H2O6 Cl3 on heating renders it colorless. Similarly, copper sulfate is white, but copper sulfate pentahydrate is blue with color. The influence of the ligand on the color, the complex. They said influence of the color. And the shades. When we keep adding, dissolving a particular nickel 2 chloride in water, if didentate ligand ethane to 1,2-diamine is progressively added, the color changes from blue, pale blue, purple, violet. This particular illustration is clearly given to explain the influence of ligand on the delta O. Am I right, ma'am?
Delta 0.
Yes, delta O, delta 0. When we say when that energy difference changes, the amount of energy absorbed and then the energy returned changes. So the shades change. The DD transition varies depending upon the type of ligand and the extent to which the ligand brings about the splitting of d orbitals, the extent of splitting of d orbitals. So CFT is the best theory to explain color. In fact, there are some questions in the textbook which is based on color. It's explained only by CFT. The question will not say use CFT to explain, but we have to encourage children to use only CFT to explain color based on the DD transitions. So what is DD transition? Coming back to how do you explain DD transition to children? Why is it called DD transition?
Electrons move from one set to another set.
Yeah, within the d orbital, that is when the degeneracy of the d orbital is lost because of the ligand. We need to understand here that the electrons can transit from one d, that is lower energy d, to higher energy d, and that on returning back emits the radiation in visible region exhibiting color. So that is what DD transition is. And DD transition, the energy absorbed or radiated will depend only on the type of ligand with which the central metal ion is bonded. So CFT is basically can be used to explain color, like this titanium complex and copper complex, very, very important. And tetrahedral splitting also only tetrahedral splitting given, and spectrochemical series is mentioned there. We don't ask children to learn by heart spectrochemically series, but water is always a kind of debate whether water is a strong field ligand or a weak field ligand. Am I right?
Yes.
There's this question in the in-text which talks about iron complex with CN and iron complex with water. An in-text question where it gives away that water is a weak field ligand. Where it says iron aqua complex is strongly paramagnetic, iron CN complex is weakly paramagnetic. Am I right? I'm just telling this out of memory because that particular page in the textbook is a blank for me. I don't have that question in the textbook. But if one of you can verify and tell me.
You are muted. Sindhu, muted.
Exalco is strongly paramagnetic, right, ma'am? You're right.
That is the question where we clearly indicates that the water does not initiate pairing up. So it is strongly paramagnetic. There, the child will know from the question. If the child has done that question, they'll know what to do with water. What happens when we have heteroleptic complex, ma'am? How do we handle heteroleptic complex in BB theory of CFT? Anybody, any insight?
Always
In the
because
textbook, homoleptic only they have always handled.
oxalate comes before in the spectrochemical series and water comes after that. So that's why always there's a doubt. No?
Yes, that's a doubt, ma'am. That's a doubt. And whenever we have a bidentate ligand, ma'am, I understand a bidentate ligand will be a strong field ligand. Am I right?
Yes,
Yes.
Yes, and this
Formation. It leads to stability.
yes, ma'am. That is what that C2O42 minus comes after that. That C2O42 minus is actually a bidentate ligand, and C2O42 minus is technically should be a strong field ligand, but it comes after water in the spectrochemical.
Yeah.
That's why children get confused. That's where we need to clarify that water is indeed a weak field ligand. Ma'am, I was asking this question about when we have a heteroleptic complex, like say NH3,4 and octahedral complex, and say Cl2. What kind of in BB theory? What do we take it as, ma'am? What kind of hybridization, say for cobalt, you take?
We go with a strong ligand, no, ma'am. Strong ligand will be considered when we have.
Yes.
Even if one strong ligand is there, we go by the strong.
Go by that, because this kind of heteroleptic complexes are not mentioned in BB theory or in CFT. They have only spoken about homoleptic complexes. Heteroleptic complexes not discussed. So when we have yes, ma'am.
Exercise, there are questions based on that, but not as examples.
Not
right?
an example. D orbital occupation they have given. There they have given. So we need to understand. We go by the strong field ligand. So are we all clear about what are the outcomes and how we cruise through this lesson?
Yes, ma'am.
Ma'am, for the copper sulfate case, we still talk about loss of
No, ma'am,
ligands.
yes, ma'am, where we say degeneracy is lost. So transition, because in copper sulfate, it's 3d9. Am I right, ma'am? And it remains that one electron getting excited to the higher 4s. So there is no d orbital to go up to. There is no dd transition possible. dd transition is not possible, but transition to 4s is possible, but that will require higher amount of energy. When the degeneracy is lost, when water is there, there is degeneracy. It is divided into 4. So that one electron can go up to, can move from orbitals. From the 4, that is the split up orbital, to 4s. That energy difference is reachable. The split up d orbitals into 4, the top, that's where the single electron will be, right, ma'am? That to 4s is reachable energy wise, and on returning will exhibit color. Whereas when it is degenerate d orbitals to the 4s, excitation.
How I normally explain is like in the cases of say D8 nickel cases, supposing it is forming an octahedral complex, then you would have T2G6 and EG2.
Correct.
So in that case, an electron from the T2G can move into the EG.
Technically, when we say movement of electron is more possible, energy taking energy from the visible region will be more possible when it's unpaired disintegrated matter.
Actually, it is like this between the T2G and EG, the energy difference corresponds to the energy of the visible part of the light. Whereas when we say copper sulfate, I don't know, I explain it this way, that when copper sulfate pentahydrate is heated, there is a loss of water molecules, ligands are lost, the degeneracy is restored. So now there will be a transition of electron from a degenerate d orbital into orbital of equal energy. So it's like a set of 5 orbitals containing one unpaired electron. So there is still a provision of excitation, but the energy required is so small that it does not fall into the visible part. I don't know whether I tell it this way. Whenever supposing I have got
when it is degeneracy is lost, all orbitals become equal in energy mass.
So, but
so
still
that one electron can move into another equivalent orb. It can move there that way also, ma'am. It can also.
Yeah, it can move, but the energy required is so small that it does not fall into the visible part of the spectrum. So it is consumed. doesn't come from the visible part.
Visible part of the region.
Yeah, like
I
for
explain it
example-
like this, ma'am. I say when the degeneracy is lost, all the pi orbitals become equivalent, and that one electron, because I focus on one electron getting excited, moving up to the 4s. We don't have that much energy in the visible region to make excited to that level. When the water molecule is lost, it's CuH2O4. When the water molecule is lost, the single electron is not able to, it probably will get excited within the d orbitals, but definitely not to a higher energy level than d, which is 4s. It doesn't
like,
fall in the visible region.
when we say oxygen is paramagnetic, we do say that there are two unpaired electrons in the antibonding pi-star orbital. So with the two unpaired electrons, yet the color of oxygen is not a peculiar one, it's a colorless gas. So in that case, like this is how I relate. Like there I say that any excitations do happen, but they don't, the excitations don't fall in the visible part of the light, and hence we
Yes.
are unable to.
Same, ma'am, in copper sulfate also, when we say color is because excitation of one electron of the split of d orbitals in presence of water, I say, could be possible when we split up the 4 into 4 and the top, the electron is present on the highest energy orbital of the split up orbitals, square planar split up, from there to 4s, that would fall in the visible region. That possibility also can be explored
Yeah.
when we talk about exhibiting color. So that is something which we need to emphasize again. Bottom line is when it's about color, it is only CFT. Best one to use is CFT. So tetrahedral splitting also is there in our textbook. These diagrams are definite questions for the examinations.
Excuse me, ma'am.
Yes, ma'am.
Ma'am, would you please give me some clarification to identify the strong ligand and the weak field ligand, ma'am? Apart from the spectrochemical series, how?
We go by, at least some of us go by the textbook exercise questions.
Yeah, ma'am, if it is given as weakly paramagnetic or strongly paramagnetic, they can use it and identify it. But if complex is given and they have been asked to mention about the ligands, how to identify them?
Ma'am, then we look at spectrochemical series, ma'am, and previous knowledge. How many exercises we have done? How many questions we have done?
Okay.
Normally what I do is I make the children to do a small modification in the spectrochemical series for this sake alone. I bring the water molecule before oxalate. I just shuffle the places and I then say that from oxalate onwards, they are all strong. And before oxalate,
They are all weak.
I first shift the position. It's a temporary shift.
Okay.
Water is brought first and then oxalate is from oxalate onwards. So that actually we are like, I tell them that we will steal information from CFT to deal with the VBT.
But never show that we stole.
Yeah, we stole it.
Correct. So this is about the DD transition. This is literally what it means. This is there in the textbook as well. This works very well. When you depict this on the board, children catch it like very quickly. So I would suggest we also make use of this. And next aspect is bonding in metal carbonyl, synergy bonding, which we already spoke about. Structure is very important of iron pentacarbonyl, and we have carbonyls of chromium also, I think, in the textbook. Yes, manganese, decacarbonyl. These structures could be asked, and the synergy bonding, the pi bonding based on MO theory, the sigma bonds and the pi bonds, very, very important, two-way bonding. We understand that a pair of electrons from the metal to the ligand and a pair of electrons from the ligand to the metal. Very important. That's where I prefer to show a depiction like this, where it's held like this, both ways. So it becomes very strong. In fact, this is the reason why iron pentacarbonyl is so much 300 times more stronger than heme iron complex, making it a deadly poison. So there they are able to remember pentacarbonyl of iron very easily. That's the reason why people die of carbon monoxide poisoning, fatal. So the bond being very strong, making it lethal for human beings. That is one place where we could talk about accidents, how to prevent the accidents, in a air conditioned garage, the garage closed and the car air conditioned on. It's another very, day-to-day relatable aspect for a child. And he says that you switch on the AC and you close the exhaust of the car. That's when deadly carbon monoxide poisons the atmosphere of the car. So you could always give a caution of that. And I think the last part, again, this is application of coordination complexes, which I'm sure all of us very clearly speak about, importance and applications. In fact, I start the lesson with this and then go on with the lesson. So that was all about coordination. Stability of coordination complex is one part where we talk about the dissociation constant, the association constant in this case, and related to the stability of the complex.